Okay, everybody's doing okay. The weekend is actually pretty cold. Okay, so on the board is actually trying to test whether you actually memorize the things I asked you to memorize from last week. Okay, so we'll just quickly refresh our memory about all these definitions. Okay, so at least actually 6 specific quantities here, right? So those are the equations that you need to actually memorize. And then first thing first. The first one is actually the mass of your solute divided by the formula weight. Oh, before I go into this, any questions for the course? Everybody's fine with all the contents. For the in-person lecture recording too, it's all black. I'm sorry. Somehow I forgot to share the screen last Thursday. Okay, and I do make sure that I do share the screen before I came to this lecture. Okay, so hopefully those things won't happen again. Okay, but I guess you can still follow. Everybody has a Hangout, right? So I think if you actually use your Hangout, you follow along, you should be able to actually get those numbers properly too. Okay, so let's do the first thing. Okay, yeah, but other than that, any other questions for the courses? For the exams? No, okay. So then we get back to this, okay? Trying to refresh our memory about the things we have learned last week, okay? So the first quantity, mass of your solute divided by the formula weight of your solute, okay? That is the definition of moles, right? So you must know these equations, okay? These 6 equations, the equation you must know by now, okay? If you haven't actually memorized this, meaning that you haven't actually put into enough effort, okay? You memorize it now, then you feel comfortable in 4 weeks, okay? So first one is actually moles, therefore you know answer A cannot be your correct answer, okay? Second term, moles of your solute divided by the mass of your solvent. That's the definition of molality, right? Therefore you know the answer has to be either, that's actually only one. The answer has to be B, right? Really easy, okay? But still, we need to actually go through all the terms so we can make sure we cover all the grounds, okay? The third one, mass of your solute divided by the mass sum of your solute and solvent times 100%. That's the definition of mass percent, okay? The fourth one, moles of your solute divided by the mole sum of your solute and solvent. That's the definition of mole fraction, okay? The fifth, mole of your solute divided by the volume. Okay, I should put in liters. Okay, let's actually definition of molarity. The very last one, the molarity multiply the number of equivalent. That's the definition of normality. Okay, so these are very important equations that you must memorize. Okay, so the answer will be B. Okay, now get back to the things we want to actually cover today. Okay, so here, this is pretty much kind of the summary of the key contents for chapter 10. We finished the first part last week, so week 1. We actually covered this. This is actually the things we want to cover today. Okay, so you see a lot of things going on here, right? But luckily, all the things we're going to talk about today is more like conceptual things, meaning that you under the concept, then you are fine. Okay, calculation-wise for this for today's lecture is actually a lot simpler. Okay, equation is always very simple. Okay, so what we're going to go through is actually we want to actually talk about this quantity called the delta H solution. Okay, everybody know? Anyone know what delta H means? Change of what is enthalpy? Energy, a form of energy, right? So typically in the old times, people consider energy in the form of heat. Okay, so energy is actually a very interesting concept. Okay, so if you get older, okay, and you are so fascinated by with chemistry, then there'll be actually one course you're going to take called the thermodynamics. Okay, so thermodynamics is actually a human invention. Okay, it's actually with anyone know like how many years that human beings have devoted our time into science? Anyone have any ideas? Like all the knowledge that you see nowadays, when did they start? Thousands of years? Any other guess? 100 years, 200 years, maybe 250 years to be more accurate. Okay, all the things you see, all the topics you see, okay, all the books you see, okay, for the modern science, it actually start around 200 years ago. Okay, thermodynamics is actually the subject that summarize humans' observations, and then from the observation, we conclude a few rules that's always true. Okay, so about 200 years ago, people start to actually get fascinated with the concept of energy, okay, or heat. Okay, so we start to actually really something that we cannot actually touch, but we can feel it. Okay, so that's actually the starting point of energy. Okay, chemistry is actually something that's very interesting, right? So how chemists think about how molecules actually store the energies. Okay, let's store the energy in the chemical bonds. Okay, that means actually if you actually break bond forming bonds, there must be some energy exchange between the process. Okay, so delta H is actually a quantity that scientists create, okay, to describe the change of energy. Okay, so now I want to think about how to actually form a solution. Okay, so to form a solution, we must have solvent and, okay, then what do? You mix them together, right? So what happens after you mix them together? You form a solution, but what does that mean? At the atomic level, at the molecular level, right? So let's use salt water as example that you can think about these things more properly, okay? So salt, what is salt? What's the chemical formula of salt? Sodium chloride, right? So sodium plus chloride minus sodium plus chloride minus, they form a periodic structure, right? Then eventually form a solid. If you see that in your kitchen, it's a white powder, right? Solvent is what? Water, right? So inside a beakers or inside a container, you see water. Water is actually a whole bunch of H2O mingled together. Okay, but don't actually bind with each other. Okay, so there's only something called the hydrogen bonds that put these two molecules close enough, but still have the freedom allow them to actually diffuse around, right? It's very different from the solid, the salt. It's very different, right? Salt is actually a very older orientation of atoms. Okay, so it's very different. Okay, now you put these two things together, you mix them, right? What happened to the salts? They dissolve into ions now. Okay, it is not sodium chloride, sodium chloride, sodium chloride in the solid form anymore, right? It disappeared. You don't see it anymore, right? When you look through the salt water solution, it's transparent. Okay, so that actually tells you something has changed. Okay, so what changes actually the salt? Okay, instead of forming this periodic structure, let disassemble itself, create Ki ions and Ni ions, right? So that's actually for the solute part, right? What happened to your solvent? So before you mix them together, the neighbor of your solvent, which is water, right? The neighbor of water is still water, right? It's water everywhere. But now it's different because right now you have sodium plus, chloride minus, right? So you have some new neighbors coming together. Okay, so once you have new neighbor comes together, what do? You start to mingle with each other. Okay, so in this process, there's actually a mixing component start to get involved. Okay, so in order to actually have the mixing to happen, we need to think a little bit deeper. Okay, let's think from the solute point of view. Okay, so for the solute, what you need to do is actually to break the solute apart, right? Originally, you have salt, means actually closely aligned with each other, right? But right now, in order to form a solution, you need to actually break them apart. Okay, so if you want to break that apart, okay, we know in the salt, what's the bond involved in forming the sodium chloride? Ionic bonds is actually very strong bonds, right? In order to pull the bonds apart, you need to give energy to do so. Okay, so the delta H of that is you need to give energy into the solute itself, right? So we define if you are giving the energies, it's plus in terms of sign. Okay, so the delta H turn of your solute is always positive because you always need to break it apart. Okay, so that's first things you need to know. Okay, how about the solvent? Do you actually break apart the solvent too? You do. Okay, but because solvent is actually not tied with each other so strongly, therefore the energy you actually put in is much smaller. Okay, so the delta H of your solute is way bigger than the delta H of your solvent, but both of them will be actually positive. Okay, but delta H solute is actually big positive. Delta H solvent is small positive. Okay, everybody follow these things? Okay, so now let's actually break apart the solute and solvent, right? Now we're actually talking about the mixing. Okay, mixing means what? Every time we talk about something is actually mixed together, that means these two things need to interact. Okay, so what happens when you actually have favorable interactions? You stabilize. Does that make sense to you? If you have a good interaction with someone else, you feel calmer, right? You stabilize. It's actually very similar analogy, okay, at the atomic level. Okay, so therefore, when you have the delta H mixing, okay, which means actually mingling together, they start to interact, okay, they typically give you a negative sign, okay? So let's actually spatial terms for each of this, okay, which we're going to talk about right now. Okay, let's go back to the hangout here. Okay, so we'll actually start to talk about this solution formation. Okay, so delta H solution is going to have three terms, but basically you can consider these two is actually the breaking apart part, right? Delta H solute and delta H solvent. Both terms will be positive, but delta H solute will be the big positive. Okay, so big positive. So this actually, small positive. Okay. And delta H mixing is actually when you mix your solvent and solute to let it interact. This typically you have a negative terms. Okay. So in CHEM1312, pretty much in this chapter, all the solution we talk about is aqueous solution. Okay. Therefore, we want to actually associate these three terms into a specific terminology you're going to hear all the time. Okay, the first thing is actually delta H solute. That term is because you are breaking apart the lattice of your solute, right? So let delta H solute, oftenly you're going to see in the questions, was actually replaced by this term called the lattice energy. Okay, it's always a big positive number. Okay. And then the delta H mixing, because it's always in the aqueous solution, right? So you're going to see this term called the hydration energy. Okay, hydration energy means actually stop interacting with water. Okay, so we call it delta H mixing. Okay, in this specific chapter, we can also replace that as a term called the hydration energy. Okay, so from this equation, you should be able to see that the sign of your delta H solution can either be positive or negative depending on the amplitude of your lattice energy and hydration energy, right? If you have a very big, very large hydration energy, if they outweigh your lattice energy, then your delta H solution will be negative, okay? If the lattice energy is actually larger than your hydration energy, then your delta H solution is positive, okay? So the question you're going to encounter for this chapter is actually going to ask you, okay, if your delta H solution is positive, what does it mean? Negative, what does it mean? Okay, so you must know the sign of different energies. Okay, specifically hydration energy, you need to know it's negative. Lattice energy is actually positive. Okay, and then the relative amplitude will actually dictate the sign of your delta H solution. Okay, so far so good. Any questions? Okay. Which one determines, so the relative amplitude of your lattice energy and hydration energy will dictate the sign of your delta H solution. Is that clear? Yeah. Oh, why do we call that? Why the delta H solute is called as lattice energy? Okay, we said what's our solute in our previous case is with sodium chloride as example, right? So when those things actually have this very specific orientation in chemistry, we call they form lattice, right? You want to actually break apart the lattice that cause energy. Therefore, we call it as lattice energy. All right, any other question? Okay, so now we want to actually come into this. This is actually a very important summary statement that you need to be actually very, very good and understand this. Okay, the first one is actually if your delta H solution is negative. Okay, so under this case, you know your hydration energy, which is negative, outweigh your lattice energy, which is positive, right? You have more negative than positive, therefore overall it's negative. Okay, so that's what the delta H solution is negative. Okay, so under this case, what happened? So here, in this case, we say the hydration energy outweighs your lattice energy, right? So that means actually when the solute and solvent, they interact, they bring your system into a lower energy state. Okay, and the system I'm talking about is actually the interaction between your solute and solvent. Okay, so you have actually some interaction that is going to bring down the energy. Okay, everybody follow so far? Okay, so once you bring down the energy of the system, we know the energy is always conserved, right? What happened to those energy that got lower down? There's actually a gap, right? What happened to those energy? Into release to the environment. Everybody follow the things I just said? Okay, so when you release this heat into environment, okay, so what is actually environment? Yeah, so think about this, okay? So under what condition you are going to have that interaction? It has to be a solute particle in water, right? So that is actually your system. You have many of these things happening inside your solution, right? However, Inside solution, what is actually the majority? Your solvent, right? Solvent is actually the big part of your solution. You have a few solute. Okay, so every single solute, you're going to have that interaction, right? And they're going to release energy. They're going to release heat. Okay, who is the neighbors of those interacting entity? Water, right? Your solvent, right? Therefore, once you actually release this heat into your neighboring waters, so your neighboring water will become hot, right? Therefore, your solution temperature is going to increase. Okay, so that's why we say the heat was released, right? Because the interaction, so heat is released. The temperature of your solution is going to increase. Does that make sense? That's actually really fundamental molecular or atomic thinking. Okay, but it all go back to this very simple concept. Good interaction bring down the energy. The energy actually release goes to your neighboring waters. Okay, so if your delta H is negative, that means actually interaction or hydration dominates. Therefore, into release heat to the water, therefore the water temperature is going to go up. Make sense? Okay. So once you understand this, once the delta H solution becomes positive, it's just the opposite. Okay, the stabilization is actually not enough. Okay, therefore, that interacting entity need to actually absorb some energy from its neighboring water, right? Since your neighboring water is actually giving out energy to that interaction, therefore the overall temperature is going to decrease. Okay, so here the key is actually to actually start to associate the sign of your delta H solution into a term exothermic or endothermic. Okay, so if it's actually negative, we call it exothermic. Okay, under exothermic condition, you know the heat was released from the interacting partners. Okay, and then the temperature of your solution is going to increase. Okay, so this is actually the things that are going to test you. Okay, so let's look at one question so you can actually see what I mean. Okay, let's read this. A flask contains solid ammonium chloride become colder as water is added and the salt dissolves. Is the magnitude of the lattice energy of ammonium chloride larger or smaller than the combined hydration energy of the ions? Okay, so here, the keyword is actually these two, right? Because the lattice energy we know is actually delta H of your solute, which is always be positive, right? Hydration energy is your delta H mixing. Okay, and you want to know the Q is what? You want to know your delta H S is larger, small, or equal delta H mixing, right? So this is actually a question that you want to actually address. Okay, so the data is what? It says when you actually mix these two things together, you see that keyword colder, meaning the temperature is dropping, right? So after you mix, once you have the solution, then you know the temperature decrease. Okay, so temperature decrease, then we need to know, okay, because your delta H solution equals to your delta H solute plus delta H solvent plus delta H mixing, right? Of course, this is small, you can kind of ignore it. But this is actually your lattice energy. And this is actually your hydration energy. Okay, so we need to actually recall the things we just talked about. okay, which I believe majority of us didn't actually memorize that, so we want to refresh our memory again. This. If your delta H solution is negative, we call it exothermic. The temperature will increase. Okay? If your delta H solution is positive, we call it endothermic. The temperature will decrease. Okay? So in the question it says, after you mix them together, it becomes colder, right? Means what? Means temperature is decreased, right? Therefore, you know, this is actually the condition you are talking about, right? Therefore, you know your delta H solution will be positive, right? Okay, everybody follow this? I'm going to go back to the question. Okay, because the temperature is decreasing, therefore we know delta H solution will be positive, right? So, because your delta H solution contributes from two terms, right? Where your lattice energy is positive, your hydration energy is actually negative. Okay, in order to have a positive delta H solution, therefore you know your lattice energy needs to be larger than the hydration energy. Okay, so this is actually the typical question you'll be asked in your homework, in your quiz, or in your midterm. Okay, so you must know that delta H solutions, okay, it's a sign, okay. If you know delta H solution is negative, it's exothermic, temperature increase, okay. If it's positive, endothermic, temperature decrease, okay. And then if it's actually delta H solution, if it's actually positive, therefore then your lattice energy will outweigh your hydration energy. Negative will be the reverse. Okay, so that's actually a key concept that you must know for this topic. Okay, any questions? We good? Okay, then we can actually come to the second big things that we want to discuss. The second big topic we want to actually talk about today is the solubility. Okay, so it is not ask you to calculate the concentration. It's just going to ask you, if I give you a few chemical substance, can you predict, okay, which one will dissolve better in water, which one will dissolve better in organic solvent, those kind of things. Okay, and then it may ask you, okay, if I actually change my temperature, change my pressure, okay, how will actually influence the solubility of my substance? Okay, those are the things we want to talk about now. Okay, so first thing first, the most common question you're going to be tested for this part is actually, if today I give you a solute in a chemical substance, right? And I ask you which one will dissolve better, okay? So here I actually highlight the basic principle that you should actually focus on, okay? So like, dissolve, like, okay? That's actually the wordings they are going to see in your textbook, okay? But these things is actually quite unclear to me, okay? So when I start to teach this concept, then I start to say, when we talk about the solubility, you always want to think about this term called the Okay, hydrophilic and hydrophobic. Okay, anyone know what these two words means? Yeah, water liker, water hater, right? So how do you know whether a molecule is actually a water liker? Hmm? Polarity? So what's the most important bond in water solution? Hydrogen bond, right? So in order to have hydrogen bond, what's the atom you must have? Yes, very good. And so these are the features you are looking for in the chemical formula. Okay, if the chemical formula doesn't contain OH, doesn't contain NH, it's not going to be hydrophilic. Is that simple enough? Yeah. So many students actually, yes. F is not hydrophilic. F is actually hydrophobic. Okay. So we'll talk about that in the, okay, we will talk about it now. How do you know a molecule is actually hydrophobic? If it only contains carbon, hydrogen, and halides, they are hydrophobic. Everybody understand what halide means? Okay, so everybody have periodic table, right? If you don't, then I suggest you actually print one out because we're going to use it a lot. Where's my? Everybody see this column 7A? Those are the halides. Okay, fluorine, chlorine, bromine, iodide. Okay, the whole column we call it as halide atoms. Okay, so if you only have carbon, hydrogen, and halides, they are hydrophobic. Is that clear? Yeah, so that's what it means by like, dissolve, like. Okay, so you must actually try to identify those specific functional group, okay, to help you to predict which one is going to dissolve better in water. Okay. So sometimes, okay, so here we see for the solid liquid solutions, right? We say polar solid dissolve better in water, right? How do you predict polarity? How polar this molecule is? Huh? I do hear the answer, the correct answer. Structure is 1 and electronegativity. Okay, so there are a few atoms. Let's think about this, okay? Answer me whether the things I'm going to say is polar or nonpolar. Okay, H2. Nonpolar, how do you know? Okay, so H2 is what? One H, another H, right? And then in between they form a single bond, right? Is the electron being pulled toward one more than the other? No, they are not, right? Because they're identical. So you cannot say, okay, electron will actually move toward me more than the other, right? So any diatomic molecules, they won't be polar because they are the same. So there's actually no preference going to one than the other. Make sense? Okay, so then how do you actually create differences? It has to be heteroatom, right? Because heteroatom, then you have a chance that you can say one is actually more electronegative than the other. Therefore, it pulls out the electron more than the other. Okay, once the electron is not equally distributed across your molecule, then it becomes polar, right? So you need to actually know what are the atoms that is actually highly electronegative, right? So what are the atoms that's actually very electronegative? Okay, so again, go back to your periodic table because it's easier to memorize the pattern. Okay. Oh no, this cannot be seen. Okay, so these are the few ones that's highly electronegative. Okay, so if you see a diatomic molecules, one is H and one is this molecules, these atoms, it will be polar because electron will be pulled strongly toward these few atoms. Okay, so that's actually when the electron activity start to play a role. Okay, but sometimes there's also some very interesting case. NH3. Sometimes structure also matters. Okay, so if you look at this, by itself, it is polar, right? But if you start to think about this, there are actually 3 arms for this structure, right? There's actually a chance that even though individual bonds, they're actually all polar, but structure-wise actually cancel out with each other. They make the molecule become nonpolar, right? So let's actually a little bit deeper understanding of the molecule, right? Which I don't think that if you're not chemistry major, that's that important to you. But that's actually something good that if you want to really understand the world at the molecular level, that's something that is good to know. Okay, so get back to here. Okay, so that's what I say, what I mean by, we know water is actually polar. Okay, so it's 1 oxygen, 2 hydrogen. Okay, it doesn't actually cancel out from each other because the oxygen still have 2 lone pairs. Let's put those 2 ions, okay, bending it down. Therefore, collectively, you still have a polarity of the water molecule. Okay. So, but if you want to actually have things that can dissolve in water, then there's actually a good, very high chance it is a polar molecule. Okay. The other very important concept we need to know is actually factors that's going to affect the solubility. Specifically, we talk about the temperature and the pressure. Okay. So depending on what the solute is, okay, if your solute is actually liquid or solid, higher the temperature, you dissolve more. Okay. I guess very easy to imagine, right? Think about like you heat up your water, you can actually dissolve more sugars. It's very simple. Okay. But it's the opposite if your solute is gas, right? Think about you heat up your Coke. What happens? All the CO2 actually goes into the atmosphere, right? You don't have CO2 inside your Coke anymore if you heat it up. Okay, so that is actually the things that you need to know. Okay, when temperature increase, then your solid solute solubility of your solid will increase. Okay, but the gas will decrease. Okay, that's what it means. Okay, so that's pretty much all you need to know for the temperature. Okay. Pressure is actually another thing that's very interesting. Okay, here we actually need to memorize one equation called a Henry's Law's equation. Okay. So what it means is that the solubility of the gas inside your solution is proportional to the external pressure of that gas multiply a thing called a Henry's constant. Okay. So this thing is also very easy to understand. Okay. So any of you have this machine called the what is it called? The soda stream. Anyone know what I'm talking about? You can actually make the bubbling water at home. No one knows? Yeah, you carbonated your water, right? How do? You have a gas tank, right? So inside gas tank is actually a high pressure of CO2. Okay, you force those CO2 goes into the water in a closed container. Okay, so if higher the pressure that you have, the more CO2 will goes into your solution, so that you have a fizzy water afterwards. Okay, so that is actually a equation to describe that relationship. The C means actually the concentration of the gas inside your water. The P is what's actually the external vapor pressure that you exert into your water. Okay, and those two will be proportional with a constant K over there. Okay, it's less simple. Okay, nothing more, nothing less. Okay. Everybody have question of that equation? No questions? Then I want to start to think about this. If I don't apply any pressures, let's say I don't apply any CO2 pressures onto my water, what's the solubility of CO2 in water? 0. Okay, so we don't have any chemistry student here. Anyone's actually a chemistry major? Okay, so in chemistry, we always want to do, sometimes we want to do reactions in the air-free condition. Okay, but we know in the ambient atmosphere, we do have a lot of CO2, right? Therefore, the water that you have will always contain some of the CO2, a lot of nitrogen, a lot of oxygen, right? So what do? You actually put those things under vacuum. So those gas, dissolved gas, will start to evaporate out. Then you have the gas-free water for you to do the reaction. Okay, so it's basically this idea, very simple, right? If there's actually no external pressure, then there will be actually no such molecule dissolved inside your water. Yes. Oh, that's different. Yeah, that's different things. Yeah. Yeah. So we won't talk about that though, but if you are interested, we can actually talk about that after the class. Okay. So this is actually the things that you kind of need to memorize it. But like I say, it's very simple. Okay. Okay, so with this being said, then we can just go through a few more questions now. Okay, so this is actually a very simple question. Okay. Which of the following is more soluble in water? Okay, the first thing is actually methanol. The second one is CCl2H2. Okay, so when I talk about these solubility things, right? So if it's trying to dissolve in waters, then the molecule has to be hydrophilic, right? So in order to actually to judge whether a molecule is actually hydrophilic or not, then to actually looking for specific functional group, right? Which is NH or OH, right? So what is methanol? CH3. So you must know this, right? So this is CH3OH. Okay, what's this? It only contains carbon, hydrogen, halide. Okay, so this one will be hydrophobic. Okay, since water is hydrophilic, therefore the molecule has the OH will be the answer you are looking for. Okay, very simple, right? Okay, so Now it's practice time. It's multiple choice. You may actually have more than one answer here. Okay, which of the following can dissolve in waters? Okay, so this question asks you the substance that can dissolve in water, right? Therefore, you're actually looking for the substance they are hydrophilic, right? Therefore, anything contains OH, NH, okay? They will be actually things that you are looking for, right? So what's the things that contains OH? Does the first one contains OH? No, it's actually pure CH, right? Yeah, so you know they will be hydrophobic, right? I hope everybody can see these things now. Should be actually quite straightforward. Second, Br2 is a halide element, right? And it only contains halide. Then it will be hydrophobic. Okay, what's the third one? Sugar, glucose, yes. Okay, so I guess many of you is actually bio major or bio-related major, right? You should actually recognize the equation C6H12O6, okay? It actually contains a lot of OH inside the equation. Okay, so again, OH rich, therefore hydrophilic. Okay, so C is definitely one of your answer. What's D? Alcohol, ethanol. Okay, you see that big OH over there? So they will be hydrophilic as well. What's the next one? NH4Cl. It is a salt. Okay, a salt. Okay. So when we talk about this hydrophobic, hydrophilic, was actually we assume you have an organic molecule. Okay. Yeah, so then you're actually looking for NH and OH. Okay. But you should also remember salt will dissolve in water. Okay, so NH4Cl is definitely a salt. Therefore, you should know that they will dissolve. Sorry, NaCl is a salt that will actually dissolve in water, right? How about the very last one, NH4Cl? NH4Cl is also a salt. Okay, remember this. NH4Cl is also a salt. Okay, we're going to come back to this type of molecules many times. Okay, in Chem 1312, which many students, even at the end of semester, they cannot recognize it is actually a salt. Okay, but remember this for now. Okay, we'll come back to that. Okay, but again, this question actually tests you whether you know that the molecule that can be hydrophilic, it must contain either NH or OH if they are organic molecule. Second is that if you have a salt molecule, then it will be dissolved in water. All right. So this is actually a quick summary of the second big topic I want to go through. So any questions so far? Okay, go back home and practice with your homework and quiz, okay? The very last topic we want to go through today is one of the most interesting concepts of this chapter. Okay, so it has a very interesting name, collective property. Okay, so every time you see these collective properties, okay, from the face meaning of the word is that the property will depending on the numbers of solute that you have inside your solution. Okay, it doesn't care about what kind of solute that you have, but numbers of the solute matters. Okay, and the things that I want you to memorize, the keyword you want to memorize are these four. First one, vapor pressure. Second, boiling point, freezing point, and osmotic pressure. Okay, if you see any of these keywords, then the way you think about it has to come back to this collective property. Okay, it doesn't really matter what kind of solute that you have. It only counts how many solute molecules that you have. Okay, so what's the basic thing you need to actually memorize is that if you have a larger solute numbers, okay, so how the way you calculate solute number is the concentration multiplied Van Hope coefficient I. I will explain what it means afterwards. Okay, but let's actually what I mean by the solute numbers. Okay, if a larger solute numbers, then you're going to have a lower vapor pressure, lower freezing point, higher boiling point, and higher osmotic pressure. Okay, so memorize this first. Okay, if you have a larger solute numbers, then you're going to have lower vapor pressure, lower freezing point, higher boiling point, and higher osmotic pressure. Okay, so let's actually, the first information I want everybody to memorize. Okay. So then we're going to talk about what this means. Okay, why, if you have more solute, then you're going to have a lower vapor pressure. Okay, so I want to think about this imaginary experiment. Okay, how do we get the vapor pressure? Yes, okay, so let's think about this. You have a solution, let's you have beaker. Okay, inside beaker, let's say you have aqueous, so only water. Okay, so if a beaker filled with water, okay, then how do we define the vapor pressure of that? It coming from what? Vapor pressure coming from vapor, right? Vapor from where? From the liquid, right? The liquid actually evaporate, goes into your air. They give you the pressure. Okay? So that's what I mean by vapor pressure. The molecule actually go up into the air, hit the wall of your containers, then create the pressure, right? If the solution is actually more volatile, then this will actually go up more easily and hit your wall more frequently, therefore create a larger pressure. Make sense? Okay. So now think about when you add in solute, what's going to happen? Okay, let's say you add in salt. That means actually add in a lot of sodium plus chloride minus, right? So at the atomic level, what does that do? So here the key concept is that the vapor pressure coming from where? Coming from the surface of your solution, right? Only those things on the surface can evaporate, right? There's no way that you're actually at the bottom of the container you can evaporate, right? When you heat up water, you always see this bubbling on the surface, not bubbling from the bottom, right? So those are the things that can actually give you the vapor pressure mainly. Okay, so right now, When you add in a lot of solute, it means actually solute is going to occupy some of the sites on the surface, right? So this will actually lead to a slower evaporation process, right? Because some of the site got blocked. Therefore, on left side, you just cannot create vapor. You cannot vaporize. You cannot create gas molecule. Therefore, there's actually no pressure will be produced. Okay. Therefore, you should know if you add in more solute molecules, then the vapor pressure will decrease. Okay. So that's actually a fundamental physical principle behind the observation. Okay, it's actually very simple. Okay. So now why do we say it is not just a concentration of the solute matters? Why do I need to actually multiply let I, which we call a Van Hoff coefficient? Okay. So remember in the previous lecture, we talked about this solute particle. Okay, it's different from solute molecule, right? So some of the substance which we call electrolyte, okay, once you dissolve, even you just throw in one of lead molecules, after dissolve, it becomes two. Okay, so that means actually it can occupy two sites now. Okay, that's why you need to have like correction factor I. Okay, so if a molecule is throwing the same concentration, okay, but once they dissolve, they become four of length. Four of the particle, they block out the sides. Then you actually further lower down the vapor pressure. Okay, so that's why you actually have like I times the concentration that you dissolve. Then there will be the effective concentration, or here we call it actually solute particle numbers. Okay, so get back down to the equations. Here, this is the equation that we want to actually know how the vapor pressure was calculated. Okay, so the vapor pressure of the solution P is calculated by the mole fraction of your solvent times the vapor pressure of pure solvent. Okay, everybody pay attention to this. Do you see this little circle on the top right corner? Every time you see that, that means it is a property of a pure substance. Okay, so in the aqueous solution, that means actually the vapor pressure of pure water. Okay, and then the things in front of that, the mole fraction of the solvent, okay, is telling you that if it's all waters, it's like a pure water where the mole fraction of your solvent will equal to 1, right? Then the vapor pressure will be whatever you measure for the pure water. Okay, but right now, when you start to actually throw in your solute, you don't have pure water anymore, right? Then you start to calculate, okay, then what's the fraction of water that I have? Okay, that is not blocked by my solute. Okay, then here you use the mole fraction of your solvent, which can be calculated by the mole of your solvent divided by the mole sum of your solute and solvent. Okay, so this is actually how you calculate the vapor pressure of your solution. Okay, so now think about this. The mole fraction of your solvent will decrease when you throw in more solute. Okay, so the more solute you add in, then the vapor pressure will decrease and decrease and decrease through less specific relationship. Okay, so this provides a very quantitative estimation how much the vapor pressure will decrease. Okay, is that clear? Any questions? Okay, so if not, then let's talk about another one. The freezing point. Okay, why you actually going to get to actually go lower freezing point, okay, when you add in more solute. Okay, The idea is actually all very simple. Okay, think about the one without solute. What happens when you actually freeze your water? Is that your water molecule need to arrange in a way. Can you still hear me in the back? Okay, I forgot to bring my battery today, so cannot do anything. Okay, so what it means actually when the things got freeze, that means actually your water molecules start to align with each other, forming an order structure. Okay, so this is relatively easy if you don't have anyone else. But now once you add in solute, what happened? Somebody is going to wiggling around between those water molecules, right? The more you have, those wiggling will actually be more apparent. Okay, so how do you actually still form ice? Is that you need to go further down. Okay, you actually also slow down those little things in between the water molecules. Okay, that's why when you have more solute molecules, in order to actually freeze your water, the temperature could go further down. Okay, so scientists actually eventually conclude this equation for us. So the change of the freezing point can be calculated through this simple equation. Okay, let's delta T F. F stands for the freezing point. Will equals to I is actually a Bank-Hop coefficient times M is actually a concentration term here. Okay, you use molality for this calculation. Okay, K is just the constant for different solvent. Okay, so that is just a constant for this purpose. Different solvent respond differently. Okay, but you can actually always see these things like you can always see this as the effective concentration times Kf, right? Where the effective concentration is just your I times your molality. Okay, so that's how you calculate the freezing point differences. Okay, it's delta Tf, not just simple Tf. Okay, so in order to calculate the final freezing point, what do? It will be the original freezing point for water will be 0 degrees C. You need to subtract by that amount. That will be your final freezing point. Okay, so we're going to apply the same concept for the boiling point. Okay, so for the boiling point, it's just opposite, right? So right now you have so many solute on the surface. Okay, to make the water fully evaporate, okay, you need to actually go to higher temperature to kind of push away those things on the surface. Therefore, you can actually really boil. Okay, so the boiling point is going to increase. And the equation-wise basis is actually the same. You still have this effective concentration, but here you need to actually use a different constant. We call the boiling point constant, Kb. Okay, and again, that's actually delta Tb, right? Therefore, the final boiling point you will be your normal boiling point plus the delta Tb. Okay. Very last one is actually the osmotic pressure pi. Okay, so this one is actually step time. Okay, so this is actually the you put a membrane between two solutions. Okay, and then depending on the concentration that you have, depending on solute concentration in each tank, okay, it's going to raise. Okay, and then if one is actually contains a lot of solute, the other one contains less, then you know they're going to, the water will actually always go to the one that contains more solute. Okay, and the pressure difference between the two, we call it as osmotic pressure. Okay, and we calculate osmotic pressure I times M. Again, this is actually your effective concentration. R and T. T is temperature, right? R is just a gas constant. Okay, by using this equation, they can calculate the osmotic pressure between the two sides. Okay, So those are the things that we need to know. Okay, but the key concept is, yes. Very good question. That's actually a thing I'm about to say, right? Which R you should use? So R, you have, people know R, typically we use 8.314, right? What's the unit of that? That's not the answer. 8.314 have the unit of joules per mole, okay? But what are we talking about is the osmotic pressure, okay? Every time you see is pressure, okay? Then the R that you use should have the pressure term, okay? So it should have the ATM per liter, okay? So they will give you a number of 0.024606, okay? So that will be actually a number you should use. Every time you see whatever pressure, it doesn't really matter. As long as you see its pressure, it's about gas, the R that you use must have the ATM terms. Is that clear? Yeah, because many students actually use the wrong R for their calculation. Okay, anything is, as long as it's actually about gas, then use the 0.0826. Okay, for your calculation. Okay. All right, so let's look at a few questions to strengthen this idea. Okay, so look at this. It says consider the solution 0.04 urea, 0.04 m AgNO3, and 0.04 m calcium chloride, which has the highest osmotic pressure, the highest vapor pressure, and the highest boiling point. Okay, so you want to know who has the right? So these are the three properties that you want to actually know. Okay, so let's the Q. Okay. So before I actually jump into this, jump to solve this problem, the things I want to think about is this osmotic pressure, boiling point, vapor pressure. Those are the keywords for what? For the collective property, right? So you want to actually know who has the largest effective concentration, meaning I times the concentration, right? That's the things that matters, okay? And then we know the larger the effective concentration, then you're going to have lower vapor pressure, lower freezing point, higher boiling point, and osmotic pressure. Everybody follow the things? Okay, let's actually things you need to actually memorize conceptually. We have a larger effective concentration, okay? You're going to have a lower vapor pressure, lower freezing point, higher boiling point, and higher osmotic pressure. Okay? So then you want to actually translate this. You want to highest osmotic pressure, right? That means what? This means actually the solution has the highest effective concentration, right? How about this? Highest vapor pressure, lowest effective concentration, right? Highest boiling point, highest effective concentration. Okay, so everybody see the logic of solving this question is really get back to that collective property concept. Okay, so once we can understand this, then we can see what's the data that we have. So the data we have is 0.04 m urea, 0.04 m AgNO3 0.04 m calcium chloride. Okay, so this 0.04 m is actually the concentration given. That is not your effective concentration, right? To calculate the effective concentration, you need to actually multiply that given concentration by the Van Hoff coefficient I, right? So now, how do we actually know what the I is? What's the I for this? Then you need to know, once you throw that substance into water, will it actually break apart? Okay, so the things that will break apart, we call it as electrolyte. Okay, so what's the feature of electrolyte? The feature of electrolyte is it will always contain a metal and a anionic species. Okay, it's very clear. Okay, so what's urea? This is actually what it gives you, right? Do you see metal here? Do you see a metal in that chemical formula? You don't, right? All you have is actually carbon, oxygen, nitrogen. Okay, no metals. Therefore, you know it is not, it cannot be an electrolyte. Cannot be. Therefore, if you dissolve one, it will still exist as one solute molecule over there. Therefore, the I will equals to just 1. Okay? Then the effective concentration will be just 1 times 0.04, which is 0.04. Okay? Everybody fine with this? Okay, move to a second one. What do you have? AgNO3. Okay. Can you see? Okay. There's actually a list of polyatomic anion you should actually memorize, right? NO3 is actually one of them. Okay. So if you consider NO3 is actually an ionic species, you can see that overall that molecule is actually neutral, right? That means actually Ag has to be positive. Okay. So this tells you, okay, you have a cation, you have an anion. Okay. So once it dissolves in waters, the AgNO3 will become Ag plus NO3 minus. Okay, so you throw in 1, but you get 1 plus 1 negative. Okay, so 1 plus 1, they give you 2. Okay, therefore, the Van Hoff coefficient of AgNO3 is 2. Okay, so once you know that, then you know the effective concentration will be 2 times 0.04. That's 0.08. Okay. Any question for this? Okay, if not, then let's go to the next one. What's the next one that we have? CaCl2. Okay, so Cl again is actually the halide group. CaCl2. Ca is actually in the 2A element. 2A element is actually once they dissolve, it always give you 2 plus charge. Okay, 7A always give you -1, but you have 2 of them. Okay, so since one molecule dissolve, they produce 1 cation and 2 anion. Therefore, you know the Van Hoff coefficient will equals to 3. Therefore, the effective concentration will be 0.12. Okay, so those are the effective concentration of all the listed 3 solutions. Okay, Then you want to use this information and go back to this. Okay. The species that's going to have highest osmotic pressure will be the one has highest effective concentration. Therefore, you know this one will be highest osmotic pressure, right? And then again, this one will have the highest boiling point, but lowest vapor pressure. Okay. The one that's going to have the lowest vapor pressure, the highest vapor pressure will be the one with lowest effective concentration, which will be your urea. Okay, so this question actually tests you a few things. Okay, go back home and think about this. Okay, but the things you need to learn is that first you need to know when you have a larger effective concentration, how those four quantity will change. Okay, and then you should know how to actually calculate the effective concentration for the given solution. Okay, knowing this will allow you to actually make the proper judgment. Okay, so we'll stop here today. Thanks.
In the solute when it breaks apart. So I can like count the particles.
Yeah, so you see, yes. So if you see the first one, AgNO3, right? Once it break apart, it becomes Ag plus and NO3 minus, right? You consider Ag plus is actually one entity.
Yeah.
NO3 minus is another entity, and you add up the two because one becomes two. Right. That's why the I is two. But the next one is actually you can produce one Ca2 plus and two Cl minus, one plus two that give you three.
I understand. Thank you. The I, what is that again? The
Right.
in the middle.
In the middle, which
yeah,
one?
The I.
Markov coefficient. Markov coefficient indicates what is actually the total number of solute particles. Yeah, so here you see, for the AgNO3, right? So you originally throw in one molecule, but once you throw in, that molecule will break apart. So the original one disappears, but you put these two molecules. Yes, yeah. So one Ag plus one NO3 minus. That's why you have two. Okay, and the third example is actually have one Ca2 plus and two Cl minus. That's why it becomes three.
Okay.
Okay. Okay. Sorry. Yes. Yes.
If I could take a screenshot of it, if I could fill it out. I didn't have my tablet with me when you were doing that,
Doing
like,
the
equations and all that.
so you can actually go to the YouTube video. You can screenshot a YouTube video. Yes, all the things is actually upload to YouTube.
Okay.
So everything I wrote here will be you can actually find it on the YouTube.
The chlorine, calcium.
Yes.
Why does it? Isn't it a diatomic? Why does it not stay as a diatomic? When it's in body.
So do you know the things called the octet rule?
Uh-huh.
Let the atoms want to have the 8 electrons, right? So Cl minus is actually 8 electron by itself already. So even though the Cl minus is actually, it's not going to enter with anyone else because it is already self-contained. I already have 8 electrons. I don't want to actually enter with someone else. So Cl minus is all by itself. It's stable, okay? And then I wrote two Cl minus means actually there's one here and one there. They don't actually interact.
It's not Cl, it's Cl minus.
No, it's actually Cl minus, Cl minus. That's two Cl minus.
This question. So the I for this, I get why here it's 3, but for this one, why wouldn't it also be 3 if it's or 4 at that? Because it's night.
No, this counts as one. NO3 minus actually is a polyatomic anion.
Oh, okay.
Okay, so you consider that as a one. Yeah.
Oh.
Yeah,
Okay.
because they have multiple atoms, but they all tie to each other through the chemical bonds. So you consider that as actually one particle.
Thank you.
I understand that for nitro
Mm-hmm.
Have the houses
Yeah, yeah.
as well as C and H.
Mm-hmm.
The only thing I'm confused on is I do see OH here, like the hydroxide, just OH
Yeah,
here.
ethanol, yeah.
But when you consider C and H for being hydrophobic properties, is that when C and H are exclusive, like it's just like carbon itself?
Yeah, so the oil that we see is actually a long chain C and H. Yeah, maybe like 15 to 20 that long will make it really, really hydrophobic. And there's actually no clear cut actually. It's actually a transition. Okay, see, if you look at this ethanol, you still have C and H.
Yeah.
But because the OH is actually a lot more powerful. So for this short chain carbon, hydrogen, it doesn't really matter. OH will be the dominant factors. Yeah, but if this gets really, really long, for example, you have 15 carbon, even though you have OH, it doesn't really dissolve in water. Yeah, so it's actually all relative things, but they won't test you on that. They will test you on the simple things. Very clear. Okay, it's a short chain and OH, then just go with the OH. Yes.
Since I guess it's like common sense, like it's a salt, so you should just understand that it can be dissolved.
Yeah.
I mean, I know that there's chlorine in it, and I
Yeah.
know that that's a halide, so
Yeah.
I was wondering if that would make it hydrophobic.
Oh, so if it's actually so here these things we'll go through this afterwards
Okay.
to discuss this a little more deeper. Yeah, but you should see that the NH4 is actually NH4 plus. It's NH4 plus. Cl is actually Cl minus, just like NaCl. It is, and it's different from this carbon bond.
Yeah.
Okay, so for example, CH3Cl, there is actually a CCl bond in between. The Cl is actually not charged, but the things here is actually all charged. Yeah, so if it's actually charged Cl minus, then it becomes hydrophilic. Yeah, but if it's actually the carbon chloride, then it is not ionic bond. It's actually just covalent bond.
Okay.
Then they will actually make it hydrophobic. Yeah.
Thank you.
Mm-hmm. Yes.
So is the effective concentration,
Mm.
effective concentration basically the same as normality, or is there?
Yeah, you can think about that. Yeah. Yes. 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 Good thinking. But the slightly differences is that because many of these collective properties they use molarity, not molarity. Yeah. So there's actually slightly some differences because the normality was defined as Van Hoff coefficient times molarity.
Mhm.
Yeah. So there's actually still some slightly differences.
Mhm.
Yeah. One's capital N, one's actually lowercase n.
Okay.
Mhm.
All right. Thank you so much.
Yes, sir.
Hey, I had two questions for
Sure.
you. So one, what did the I stand for in those equations?
I is just we call it Van Hoff coefficient. Yeah,
Oh.
it doesn't actually stand for anything. They just simply use traditionally.
Okay.
Mhm.
The second question is when you were solving for a Eura, right?
Mm?
Where did you get the coefficient from? Because there's an equation up there.
Yes.
You found.
So when I say if you want to have an I other than 1,
Mhm.
you must have a cationic species and anionic species.
Okay.
And if you look at the formula of the urea,
Right.
it's only oxygen, nitrogen, hydrogen,
Mhm.
right? There's no way they can form this cationic species.
Okay.
Yeah, or ionic species. Yeah,
Mhm.
and both need to be layered so they can actually dissociate and then produce I larger than 1. Yeah, since the urea cannot do that, therefore you know the I must be equals to 1.
Thanks,
Mhm.
sir.
I hope that makes sense.
So I was wondering the same, and I asked someone. So for that one, you can also look at the ionic charges, right? And they cancel out. That's why it's 1 for that one as well. Like the ionic charges.
Yeah,
Like
which
the
one?
periodic table for
Yes.
this one.
We're going to
And then-
talk about that actually a lot more
Yeah.
in later part of the class.
Yeah.
Yeah, but you're actually ahead, which is good.
And-
Okay.
And then because you do the other two, and it's 2 for that one, and it's 3 when you look at the ionic charges and add
Yes.
them up and
So
stuff.
it's not adding up the ionic charge, but adding up the coefficient in front of the species.
Right. Okay. Yeah.
Right.
So when you move that
Mhm.
one, it'll be so it'll be 1 and then 2. You have 2,
Mhm.
3 for that one. Okay.
Mhm.
Yeah.
Yeah, it's actually the numbers of atoms, not the charge itself.
Okay.
Yeah, so they need to actually make
So
sure that
there's 1A and then 1
yeah,
one
yeah.
other.
It looks like they have some correlation, but it's not, right? You just need to actually conceptually make sure it's actually correct. That it's actually we're counting the number of particles,
Okay.
right? So the particle like very likely to carry charges, right? But we're not counting the charge, but counting how many particles that you have. For example, the second one, right? 2Cl minus, right? Like 1Cl2, CaCl2 become 1Ca2 plus 2Cl minus.
Yeah.
Right. It's actually 1Ca2 plus particle, and then 1Cl minus particle, and another Cl minus particle. And we're counting that the I equals 3 is because you have 3 particles coexist inside your solution.
Okay.
Has nothing to do with the charge itself, but number of particles.
Okay, that's existing inside the solution.
Mhm.
Okay.
Make sense?
Yes, sir.
Cool.
Thank
Hi.
Question.
Sure.
So my first question is, kind of just a curiosity question. So I know that ionic bonds, they ionize in a solvent. They, disassociate. Why is it that the covalent, sometimes with covalent, don't dissociate? And because in my head, it's like the covalent bonds are weaker than the ionic bonds.
Yeah, why don't they dissociate,
Yeah.
right? So it actually all comes down to the interacting partners. So for the why the ionic bond dissociate easier in the aqueous solution is because when we talk about this lattice energy, you break it apart, right? The things that come after that is actually they're going to interact with all the water molecules. Okay, and then water molecule will actually make those charge kind of like spatially separate from the interacting partners. And then they will actually bring down the energy actually quite a bit, which is comparable, sometimes outweigh your lattice energy. So make it become actually even more stable states. Okay, so in the nature, we always go to the stablest state, right? So even though we know the ionic bond is actually very strong, okay, but after you break it, then somehow you can create a situation that can even lower down the energy, then that thing will happen. Okay, but this is actually not the same for the covalent bonds, because those covalent bonds molecules, okay, they don't actually really separate the charges. Okay, the reason that the hydration is actually very effective is because the water also like those charged species. Okay, now right now, since your covalent bond cannot actually, they don't like the charge, they don't like the charge form. Okay, therefore, there's actually no intention for them to first separate from each other. Second, since we cannot reach that state, then the interaction, the hydration is not going to have any effects to further stabilize the whole system. Therefore, it just won't happen. Yeah, so that's why even though the covalent bond is not as strong as the ionic bond, right? But since you can actually reach to that, you can hop over the activation energy, then it will never ever happen. Yeah, we'll talk about the activation energy in chapter 11. Okay, they will actually help you to understand why, yes, the covalent bond is actually weaker compared to the ionic bond by itself, right? But it's only compare, you only have this. You don't consider any subsequent interaction. But in solution, it's different. It's not just break it apart. You also consider the interaction part with the water, right? It's actually the interaction part with the water so strong, therefore breaking apart the ionic bond become visible. Okay, but for those compound only have the covalent bond, they don't like interact with water. Therefore, there's no reason they want to actually break themselves apart.
So it's basically just covalent bonds don't interact strongly with water, and that's
Yeah,
they
yeah.
stay.
They stay. Yeah.
And then another thing is you were describing how the osmotic pressure goes up with the solute particles. And I know, osmosis is like flow through a semi-impermeable membrane,
Yes.
but I'm just a little confused as to how increasing the particles increases the pressure. Because is it just because there's more solute particles that go through the membrane and then increase the pressure, or is that the process? Because it's easy for me to think about the freezing and the boiling. It's like blocking, but like, the osmotic pressure, I'm like kind of struggling to think about that.
Yeah, I kind of see what you mean here. So let's think about this. You have semi-permeable between two containers, right? So if it's all water, then the pressure will push down, okay? And then you're going to have a pressure evaporate, basically the same, right? And then two things will actually be equal, right? So right now you actually start to have a lot of stuff on one, but not the other. Okay, that means actually this part, the vapor pressure will not be very high, right? So this pressure will actually push these things down until they reach a balance. Yeah, therefore the way you do that is actually you keep pushing more water to the one contains a lot of solute. You want to actually increase the surface water population. Yeah, so that's why this actually needs to go down. Okay, then once you have this differences, which is osmotic pressure, right? Then the real pressure on both sides will be this actually the original pressure, right? And then this actually the pressure plus the weight of your water. Okay, and this will actually equal to the overall pressure on the right. Yeah. So again, it's kind of go back to the vapor pressure type of things, because right now, once you have solute, the vapor pressure is not going to be high enough, right? In order to actually increase that, you just give it more water. Yeah. And then once you have more water go through the other side, then it's going to go up, right? So these two things will happen. Once it's actually you increase the vapor pressure, that's one, okay? But at the same time, you increase the weight of the water compared to the other side, right? And then the overall will actually eventually, the two sides need to reach equilibrium at the very end, right? So that's why the vapor pressure is going to proportional to how many solute particle you have on the left. Yeah. So I don't know whether that actually, I guess that is, yeah, that's actually a fundamental reason. Yeah, I hope that makes sense.
Okay.
Mhm.
Yeah, that kind of that
Mhm.
did help a little bit.
Mhm.
I think this is in the textbook for chapter 10.
Mhm.
So I understand what a colloid is, but I mainly, because I know it's just a suspension
Mhm.
in a solution,
Mhm.
but the textbook described how they form and why they don't interact
Mhm.
with the rest of the solution.
Mhm.
And I was just a little confused by how just the process of this coagulation. I kind of understand why heating would, just because it kind of moves it, I guess, and increases the solubility, but I don't understand why adding an electrolyte would neutralize the layers and make it easier to, mix.
So colloidal solution typically happen when the particle is actually very small. Typically, it's actually a few nanometers, right? So what it means actually is the surface contribution will be very big. Okay, so charge is going to play a big role there. Yeah. So if you put in things in the electrolyte, it means actually you throwing a bunch of charges surrounding the charges. Okay, then these things will actually kind of neutralize the original behavior. Yeah, does that make sense?
Yeah.
So charge is going to play a big role when you actually go down to very small. And it's very clear, right? Because when the charge doesn't like to be, the same type of charge, they don't want to be too close with each other, right? So when the things actually get very small and you still want to put the charge on it, then the repulsion force will be actually very, very clear, right?
So
And then
it kind of knocks it out
yes,
in place.
yes, and then the solution will also play a big role now. Yeah, because any charges will actually have profound effects on whatever process you're actually looking at now. Yeah, so many things will only appear when you push the dimension of the system into nanometer scale. Yeah, when we push, say, every time we talk about things in the nanometer scale, the first thing to think about is actually then the surface charge is going to be very, very important. Yeah, way more important than whatever we see in our daily life. Yeah, it's very interesting phenomena.
Yeah, I was very interested by it.
Mhm.
That's what I wanted to ask.
Mhm.
And that's why you say, because the charge matters, when the ions have multiple charges, that's when the deviation
Yes.
from I,
Mhm.
because it changes how,
Yeah, so you cannot just simple. So the things we say here is all very simple, right? So it's kind of like, okay, it breaks apart into two, then therefore I is equals two, right? But in real world, it's actually a lot more complicated than that. This actually provides you a good first layer, big picture type of things. But if you want to really think about things at atomic levels, then the charges, many things are going to come into play, right? So predicting how it will behave will become less predictable. Yeah, so maybe sometimes is factor A is actually a dominant factor, sometimes it's actually factor B. Yeah, and they will actually depending on the context, right? The setup of your system become actually critically important to give you a reasonable answer.
Right.
Mm-hmm.
And the charge
Yeah,
matters.
charge matters a lot. Let's put it this way. Okay, so something you can say for sure is actually once the surface area become very big, charge become critically important. Yeah, positive charge and negative charge is going to give you very distinct behaviors.
See. And you said they form because they're really small.
Mhm.
And they all, I guess that was
The surface area
my
is going
last
to
question.
get very big, right?
Mhm.
So if you have this big ball, then the surface area is, you can calculate this,
Mhm.
right? But if you can normalize to its volume, it's quite small. If you have a very big ball, right? But if you actually make the ball like this big, then suddenly the surface area maybe is actually equal to your volume. Yeah, so the change of surface area is actually always a big thing in chemistry world.
So
Yeah.
that's why it forms into the line or the suspension thing.
No, suspension thing. I want to actually be careful about like what you're actually asking.
Like, because a colloid is a suspension of tiny particles
Yes.
in some medium.
Yes.
So how does that form? That was like, I guess that was my question.
Yeah, so this actually also kind of like the way beyond the scope of this course.
Yeah.
Okay, but when we start to see this nanoparticle to form, typically it's actually a few atoms. Okay, they collide with each other. Okay, and they are semi stable. Okay, they are semi-stable is because the surface charge is actually too big. They want to actually start to integrate some other atoms together. Okay, and then but in the solutions, you not just only have those things that can nuclearly can grow. Okay, there's also a lot of like surfactants trying to stabilize the particles. Okay, so there's actually a fine balance between all these thermodynamic properties between your the particle you want to grow and then the surfactant is going to attach to, and then eventually they come to an equilibrium, and then they'll actually typically have specific size will survive. It's not all the size will actually survive. It will be a specific size. But once it's actually too small, you have too much charge. Okay, and the surfactant actually have no way to actually recover those surface and to cancel out the charge effects. Okay, and then what's going to happen is actually they want to actually grow a little bit bigger. Okay, so that the surface charge they can be pushed away a little bit from each other. Okay, and once your surface actually get larger, then the surfactant can start to attach to the surface.
The surfactant.
Yeah.
Yeah.
Yeah. So those surfactant is actually basically just a long chain organic molecules, but they can still interact with the particle you want to grow. Yeah. So people actually identify this phenomenon starting from the gold particles. They just put in one gold, another gold, and start to attach it. Then you start to feel like, okay, the gold want to actually form a specific size, and then it will go under. If you increase temperature, they will go up a little bit, but it will stay there after a while. Yeah, and then they realize that there's actually they call it magic size, where all the surface charge things actually come to a balance. Yeah, and then all this surfactant will actually cover the surface of the gold nanoparticles. Yeah, so it's many things that's going to come into play once you go to a very small dimension. But you can just simplify that into the surface charge, right? And then the surfactant stabilization of the particles. Yeah. And then those things will actually come to a harmony situation. And then when they come to end, then you see this small particle with a dimension around a couple nanometers to form. Yeah. And then they have all these nanoparticle properties. All these things happens in about like 20, 30 years ago. Yeah, people see this thing for the first time around 30 years ago. Yeah.
Okay. That's super interesting. Thank
Yeah,
you.
it is. It is. Yeah. So many of the chemistry faculty they're actually working on the nanoparticle too. Yeah, especially the faculty from Rice. Yeah. Yeah. So many people actually working on this specific domain. Yeah.
Okay. Thank you. I'm gonna definitely ponder on that for a long time.
Yeah, I mean you can read more. I mean it's fascinating, I think. Yeah. Yeah.
Okay. Thank you. Well, that was all my questions for today.
Cool.
I appreciate you, man.